Welcome, everyone. In this talk, we can take a look at how you can do flexible and analytical queries on streaming data with Flink, Hudi, and Presto. We have two speakers in this presentation. I am Danny, and now I'm working for Onehouse. I have a long time experience working for open source, such as the Apache Hudi, Apache Site, and Apache Flink. Another speaker is my colleague Sagar. Sagar is a committer of Apache Hudi. He worked for Amazon and Oracle before joining the Onehouse. Let's get into today's agenda. We start by describing the challenges of streaming dataset on Lakehouse technology stack. And then we discuss the solutions from Flink and Hudi integration. In the next section, we take a look at how to unlock query with Presto and Hudi. In the end, we will also show an illustrative demo with Division, Kafka, Flink, Hudi, and Presto.
Danny, sorry to interrupt. Yeah, you might want to
okay, sorry.
The full slide. That's fine. Yeah. Keep going.
Okay, let's start by the challenges with streaming on data lake. The first challenge is the changelog stream ingestion. Recently, change data capture tools like Division got more and more widely used for capturing the database events committed from other applications. While in data warehousing, the CDC capture technology can be used for real-time syncing as a mirror table from the database onto the file system. We can then take advantage of low cost and high scalability of the storage on cloud. We can do flexible ad hoc analytical queries from this mirror table. Ingesting changelog stream into a file system storage is a tricky issue for years. First of all, the files located on file system are very probably immutable. The file format you choose may also be immutable, like the Parquet or the ORC format. This made us must think through how to apply all the changes to these files because they cannot be modified in place. Besides that, the files are committed in higher frequency from streaming ingestion job. People usually have minutes time interval to commit new files to the storage. The file numbers is soaring. These files are small files in Notion too, because records reception in minutes can really be large. This results in tremendous number of small files on the storage if no compaction or clustering are included. The second challenge is the changelog stream materialization. You probably already know Flink as a stateful streaming engine. It's good at streaming ETL. The changelog stream is the first class notion in Flink, which is also known as the dynamic table. The dynamic table records can be accumulated with computations, then propagates as another dynamic table. But there are some drawbacks. Firstly, the dynamic table is only a changelog stream. It can only be handled by Flink engine. Any other engine that the user wants to query or you do some analytic job should do some syncing into other external storage first. And secondly, the dynamic table cannot be shared among multiple jobs. Some computation operators like the SQL join are very costly for resource. It would save much money if the intermediate result can be shared. And there is no history snapshot view of the dynamic table. Also, no schema evolution. The third challenge is the incremental ETL. If we want to make a medallion architecture in streaming style, there is the producer and the consumer. Both of them are streaming pipelines. The buffer message queue is pure files on the file system. We need to meet these preconditions if we want to make it robust enough. First of all, the preservation of the event sequence is very critical for streaming computation. Engine like Apache Flink has no built-in support for event time sequence when handling the changelog records. If the records are in this order and do not comply with the real event time sequence, the accumulation result could be wrong. And both the writer and the reader job need to have the exactly one semantics to keep the correctness. The reader also needs a good manner to bookkeep the consumption offset so that it can recover in more lightweight style. Let's see how Flink and Hudi addresses the problems. We all know that Hudi has a pluggable index layer that can index the new records in record level. Each record that writes into Hudi would be tagged with the location information first, and the dataset is organized as a tree-style file layout with integral file groups. All the changes of one record key are routed inside one file group, and the file group is also the granularity to trigger compaction and clustering. And new inserts are written into small file groups with higher priority. For Flink and Hudi, we implement a record level index, which is backed by the Flink state backend. The state backend stores all the indexes of the table. The table source records can be handled in real streaming style by record level. And this diagram shows a basic ingestion pipeline for copy and write table. The bucket designer is the operator to index each record. And the stream writer is the operator to buffer and flush the records to disk. For merge read table, additional sub-pipeline like the compaction may also be included automatically. So in order to resolve issues of dynamic table, Hudi can be used as the medium for materializing all the changes. Hudi would also take care of the event time sequence and persist all the change operations. As a Hudi table, it has more promising features compared to the dynamic table. The Hudi table can be exposed as a snapshot view that can be curated by all kinds of ad hoc engines. The Hudi table can also do time travel and incremental queries with specific timestamp start point. And it can even work as like a message queue. A streaming reader can consume and replay all the changes to compute and propagate the changes to the downstream. So if we want a medallion architecture with streaming style end-to-end, a crucial issue is to resolve is the incremental consumption from the Hudi source. The first question is, in what granularity the source makes the new dataset visible to the downstream? Because the writer commits the dataset in separate commits in Hudi, it is natural that the incremental datasets are sent to the streaming reader in Hudi commits. And Hudi has a timeline to manage all the commits. It has a file system view to manage the visibility of all the files on the file system. Only files that are committed can send to the reader. The second question is how to retract the intermediate handling if there is a job failover. The incremental dataset information are abstracted into splits. The streaming reader would bookkeep the offset of each split it has consumed. Once the reader task got recovered, it would continue with the partial offset from the last successful checkpoint. The streaming reader can have a specific start offset to consume from, like the earliest offset. If the user specifies the offset as earliest, and then it can get the full dataset from the table. This is actually the medallion architecture looks like with Flink and Hudi in streaming style. So Hudi is actually the carrier of all the change logs. It bookkeeps all the change operations and do like the accumulation job, and the reader can consume from the Hudi table and propagate the changes to downstream. So we have an end-to-end streaming style, like the incremental ETL. Okay, now let's welcome my colleague Sagar to take over the left sections.
Yeah, thanks, Danny. I can
okay. I will
share
start
my screen. All right, let's begin. I want to start with the Hudi tech stack on cloud. Like any data pipeline, there is a source, there is a sink. Source can be your transactional databases. It could be event streaming systems, some files lying on object storage systems. while your sink could be some analytical engine to query the data. Um, but it's what Hudi does in between is not just simple ETL from source to sink, but it provides on top of that ACID guarantees. It provides incremental querying capabilities, time travel capabilities, and then managed table services running in the background, which optimizes the storage layout, and multimodal index, which is crucially used in query engines as well. We'll look at it in a minute. So Hudi provides this complete lakehouse platform, and you can think of Hudi like a thin database kernel on top of lake storage. So you start at the very bottom. You start with the distributed file systems or object storage systems, and you have files in open formats like Parquet, Avro. What Hudi does that it's not just a table format, but goes beyond being a table format. It runs compaction in the background for you, given that Hudi's design is more akin to log structured storage systems. It provides you the capability to build indexes. It supports two different models of concurrency control mechanism. It also has a separate meta server, which is then used to sync all metadata. And subsequently, all of this is utilized by the query engines, or all these different services can be utilized by the query engines. So from this whole transactional database layer, I want to talk a little bit about the indexes, the multimodal indexing subsystem in Hudi. Hudi has a metadata table, which itself is a Hudi merge on read table. So inside the data table, you have, so this is your data table. Inside that, you have a metadata table, which is a Hudi table. And that is where we maintain different kinds of indexes, such as files index, column stats, Bloom index. We'll see how these indexes are utilized in the query path. The cool thing about, well, this is nothing new, right? So anyone with working with traditional database systems, they can relate to this very easily. The cool thing about Hudi is that you can build these indexes concurrently without blocking the ingestion. Hudi has this async indexing capability. So how do we use Presto to run ad hoc query on streams? On a very high level 10,000 feet view, it's more like you have Hudi metadata on some storage. You need to sync that metadata to metastore. In this case, let's say Hive metastore. And then your Presto coordinator, essentially the split manager, that pulls that metadata and which helps in deciding the splits in generation of splits, which are then sent to Presto workers. So this is like what any connector would do. This is nothing special about Hudi. But I want to highlight some special things about Presto as well as Hudi. So Presto, first of all, it has a beautiful set of these connector SPIs, which makes it easy to integrate other systems. And it's highly scalable to thousands of workers. What Hudi provides is a very fast merge on read operation. So the load that we do, it's not as if we have to recompute it. We just pull in incremental changes, and we apply those incremental changes on top of the existing snapshot of data. It also provides a rich set of file system view APIs, which are used inside Presto. As I mentioned before, that Hudi has this log structured storage design. So we have multiple versions of the same data. The file system view APIs help us to filter out what's needed. What's the latest snapshot? Say if you're doing time travel query, then what was the snapshot back in time? And of course, the metadata indexes that we have talked about, which are utilized in data skipping. So let's talk a bit about the data skipping. So Um, this right-hand side in this diagram is all inside Presto module. And here is in Hudi module, split manager. Uh, Split manager has domain of some column handles, which has your predicates, query predicates. When a query comes, it goes through the split manager. So those predicates are passed on to the Hudi file skipping manager, which then queries the requests the metadata reader. Uh, uh, Given the predicates, the metadata reader will just read candidate entries from the metadata index. This example I'm showing for column stats index. So column stats index has keys in this format: a column name, partition name, and the file ID, and it stores min, max, null values. Um, uh, when metadata returns the candidate entries, that's when the file skipping manager um, is able to generate the splits, which are then passed on to the readers for further processing. The key thing here is that there is two levels of data skipping. First, we use the files index to prune the partitions. And then once we have uh, found out what partitions need to be scanned, uh, column stat index helps in skipping data within those partitions. Um, so this, as we'll see in the subsequent benchmark, I'll show you that this greatly enhances the query latency. Right now, this PR is yet to land. You can check out this PR. It's as simple as just setting one session config, assuming that you have metadata table enabled in Hudi. We ran a benchmark for GitHub archive data, 6 months data, 220 GB, 450 million records. And we were able to see quite impressive numbers here. So this blue bar is without any optimization. The red bar is linear sorting. Linear sorting means that you simply sort by a field. Um, uh, while there are techniques based on space filling curves, such as z-order sorting, z-ordering, where it's helpful when you have multiple columns in your predicates. So as you can see, that if you're querying just by primary column, z-order is not much better than linear sorting. But if you have two columns along with primary, there is a secondary column, you can see z-order doing much better. And this chart shows the amount of data scanned. So on the PR, we have run another benchmark, star schema benchmark, that also shows quite impressive numbers. To end this talk, I want to quickly show you a demo, and which ties all these systems together. So let me just stop sharing here and share the demo video. Swear. All right. I hope the demo is audible to everyone. Insert update, which generates certain change logs, which are then consumed by Debezium Postgres connector running on this bottom right screen, and which are subsequently consumed by the Flink in a Flink table, and we write a Hudi table which syncs to the Hive meta store, which can then be queried by Presto. So here I have on top left, I have Postgres. On bottom left, I have Flink. On bottom right, I have Debezium Postgres connector, and top right, I have Postgres. To save some time for the demo, I've already created a table, users table, which has these three records. And I have set up the Debezium Postgres connector, which has already consumed these three records. So if in my local installation of Confluent, if you go and look at this topic, it has already consumed some records here. Let's do one thing. We'll insert a record here. But before that, let me create a table for table in Flink to consume records from Kafka. So I have all the DMLs here, and later on I can share this with you so that you can try it yourself. So this same schema as the Postgres table, and let's see what happens when we create the table here. So the important thing to note here is that you provide the Kafka broker schema registry URL, the format, and of course the connector name has to be Kafka. So now if you do a select star from topic users, you get so this will take some time to refresh. Let me meanwhile the copy. I want to show you in this demo an insert and update. So I have already prepared the statements here. We are going to do an insert, and you can see the records here, right? RM123, fine. Let's do an insert. Now you did an insert. See, the Debezium connector consumed that. It picked up the LSN change, and now it's reflected here, right here, right? So now let's see. We'll create a Hudi table, for which again I have the scripts ready here. Again, it's the same schema. The important thing to note is that you specify the connector name as Hudi, you specify some base path, you specify the metastore URI and database and table name if you want to sync, if you want to be able to sync to the Hive metastore and query through Presto. So that's what we are doing in this DML. And this DML as such doesn't do anything. It just adds the table to the catalog. The main job that runs happens through this insert into command, and it will submit a job to the Flink cluster, which we can monitor in the Flink UI right here. So yep, this came up here, awesome. And you could also, let me show you the change here. So this base path, right, this is where we are writing the Flink, the Hudi table on this base path. As you can see, there is one Parquet file written just now, and so let's go to, this was users demo table, and we go to the metadata. You can see that there is a commit happening here. All right, so let's move to the Presto. Let's see if it's synced properly. So I'm already in Hive default schema, and previously I had these three tables. I created one new table, as you can see from this config Hive sync table name, and here you go. You have this new table. If I do a select star in Postgres, what do you get? We get 4 users. And now if I do a select, I actually just want to select, I have it here. So let's see. Otherwise, you'll be shown the meta fields as well, which will blur the screen. All right, so you have these 4 records here. Now let's say we want to update some record. Let's say we want to update this very first record with user ID 3, right? And we want to update the last login time, which has changed since the user last logged in. So let me copy the update command, and what I'm going to do is for user 3, the last login time is something 2015. All right, same date. I'm just going to change it to, let's say, user logged in after 1 hour. So this is what your transactional system is setting, giving an update here. So this again will write the change log, which will be consumed by the connector, as you can see here again, right? So this connector will subsequently, so this would have created, if we go back here to the Hudi base path, you can see that there is a commit in flight. This should have completed, and yep, so this has completed. Another in-flight instant generated. If we go up one level above, we have one new Parquet file, which is the updated, the latest snapshot of the table. And now let's query this table through Presto, and let's see if the change has reflected. So what you see here for RM3, the last login, well, the timestamp formats are mixed up, but you can see that the last login here, it's something 28, 8, 22, 26, 40. This is 62640. So this has certainly updated. So that's what I had for demo. This whole thing is very scalable when you're doing it. The important point to note here is that we didn't really resync again here. The Hudi Flink integration incrementally pulls data every time, and it automatically gets reflected on Presto. So this end-to-end pipeline is very low code, low touch pipeline. And as a data engineer, you don't have to do. All right, so that was the demo. And before I end this session, I just quickly want to talk a bit about the community and what we have in the roadmap. So we want to add first-class support for CDC data and incremental queries in the Presto Hudi connector, record level index support. We are also building some set of new table and merge APIs for easier integration with the analytical engines. And then, of course, so far the Hudi connector can only query the data. We want to add DDL support too. These are some resources that you can use for diving deeper into Hudi Flink integration or Presto Hudi integration. And our community has seen a phenomenal growth since 2020. To engage with our community, just scan this QR and you'll be directed to the right link. That's all. Thank you. I'll open the floor for questions now.
Yeah, just in case you guys missed that, we also have a Onehouse booth if you want to follow up.
All right, I do see a question here. What was that UI you were showing the files in the demo? Was that Flink UI? There was a Flink UI as well. That's the default. The cluster web UI is running on. If you launch your Flink cluster, it's there. But I guess you want to know where I showed the Parquet files, right? That's just, I'm writing it down to local file system, so I was able to open that up in Chrome. Nothing special about that UI. All right, I guess that's it. Then thank you all for attending the talk. And yeah, feel free to join our community, ping us on Slack. Will resolve your queries. And in case you want to reach out to us directly, I guess you should have the email on invite. I'm not sure. But yeah, I'm happy to resolve any queries offline as well.